Hi folks, I'm Dan Fullerton, and today I want to talk to you about electric potential and electric potential energy. Specifically, we're going to focus on point charges today. Our objectives are going to be to determine the electric potential due to point charges, to determine the work done on a charge, determine the electric field given a sketch of equipotentials, to determine the electric potential difference between 2 points on a line, and finally to state the relationship between electric field and electric potential. To begin, we're going to talk about electric potential energy, and we're going to define it in terms of 2-point charges. Let's assume that we have a point charge Q1 fixed at some point in space. We're going to grab another charge Q2, some distance infinitely far away from Q1, so that its potential energy infinitely far away we're going to define as 0. Now as we bring that charge closer and closer and closer to Q1, we're going to have to do work on it. We're going to have to push against the force, the electric force, over some displacement, so we do work. And the work we do on that charge is going to be its potential energy. So here's Q1, here's Q2. The electric force, assuming Q1 and Q2 are positive, is in the opposite direction of the displacement of Q2 as we move it closer and closer to Q1 until it's some distance capital R away. Let's find the work done in bringing that charge to that point. So work is going to be the integral from our variable r starting at infinity up until it gets to capital R of minus the electric force dotted with dr. Why negative? Well, the electric force and the displacement are in opposite directions. Or we could rewrite this as the integral from capital R to infinity, switching my limits, of the electric force dotted with dr. Switch the limits, I can switch that negative sign. So that's going to be the integral from r to infinity of the electrical force 1 over 4 pi epsilon naught Q1 Q2 divided by r squared dr. Now we can pull the constants outside the integral sign. So that's Q1 Q2 over 4 pi epsilon 0 integral of r to the negative 2 dr from r to infinity. Well, when I integrate r to the negative 2 dr, I'm just going to get minus 1 over r. So that implies then that the work we do is equal to, and we still have our Q1 Q2 over 4 pi epsilon naught times minus 1 over r evaluated from r to infinity. And when I work through that, I'm going to find then that the work I do, which is equal to the potential energy now of that configuration, is equal to 1 over 4 pi epsilon 0 Q1 Q2 over capital R. So we've found the electric potential energy due to a point charge. Notice that the potential energy is independent of the path we take. Since the electrical force is a conservative force, it doesn't matter whether we go in a straight line or we zigzag all over the place. It only matters what the starting and ending points are, a conservative force. All right, let's see if we can't find the electric force from electric potential energy. If you recall from mechanics, we could find that the force is equal to the opposite of the derivative of the potential energy with respect to L, assuming we have a conservative force, and in this case we do. So that's going to be minus the derivative with respect to R of 1 over 4 pi epsilon 0 Q1 Q2 over R. Constant over here, 1 over 4 pi epsilon naught, Q1, Q2 are also constants. So that's going to be 1 over 4 pi epsilon naught, Q1, Q2, and the derivative of 1 over R is going to be negative 1 over R squared, cancels with the negative. So I get an R squared over here. So now we have just gone the opposite direction to find Coulomb's law again, the electrical force from our definition of electric potential energy. Let's take a look at the electric potential now due to a point charge. Electric potential, which we also call voltage, is the work per unit charge that's required to bring that charge from infinity to some distance r from a point charge. So we started off with electrical potential energy. The electrical potential energy per unit charge is what we call electric potential, or more commonly, voltage. So voltage, electric potential, capital V, is going to be the work done divided by that charge, or 1 over 4 pi epsilon 0 times our charge Q, make that a little darker, Q, times Q1, Q2 over R. Or our charges are going to cancel out, and I'm going to end up with 1 over 4 pi epsilon 0 Q divided by capital R. Potential due to a point charge. And if we have multiple charges, well, voltage or electric potential is a scalar. All we have to do is add up the electric potentials to each of those individual charges. So potential then is going to be the sum over all the charges I of 1 over 4 pi epsilon 0 Qi over Ri. Or again, 1 over 4 pi epsilon naught is still a constant. Sometimes we call that K, 9 times 10 to the 9th Newton meter squared per Coulomb squared. So if I pull that out, 1 over 4 pi epsilon 0 sum over all I of Q over R. There we have our potential due to several point charges. Now, when we draw the electric field and electric field maps like we were talking about previously, we can also draw equipotential lines. Equipotential lines are just surfaces that have a constant potential, very similar to lines of constant gravitational potential energy or topographic altitude lines on a contour map. You can do the same thing, the same analog when we're talking about electrostatics. Equipotentials are lines of constant electric potential. They are always perpendicular to electric field lines. They always cross at 90 degrees, and the electric field points from high to low potential. So if we have a positive point charge here, the electric field lines are shown in black. The red lines, the red circles, those are equipotentials. The equipotentials always cross the electric field lines at 90 degrees. They always run perpendicular. And the work done in moving a particle through space is zero if its path begins and ends on the same equipotential line. Over here on the right, we can look at a dipole, a positive and a negative charge. You can see the electric field lines in black again, and the bright pink shows you the equipotentials, always crossing the electric field lines at 90 degrees. Let's see if we can't find the electric field from electric potential. If potential is 1 over 4 pi epsilon 0 Q over R for a point charge, then the rate of change of potential with respect to R, the derivative, must be the derivative of 1 over 4 pi epsilon naught Q over R, taking the derivative of both sides. Well, that's going to be equal to, well, we can pull the Q over 4 pi epsilon naught out of the derivative sign. It's a constant. Q over 4 pi epsilon naught. And then I get the derivative with respect to R of 1 over R, or R to the negative 1. So that's going to be negative Q over 4 pi epsilon naught d over dr of R to the negative 1. Which implies then that the derivative of V with respect to R must be equal to minus Q over 4 pi epsilon 0 R squared. And if we multiply both sides by R hat, a unit vector in the R direction, we can say that dV dr times the vector, unit vector R hat, equals minus Q over 4 pi epsilon naught R squared times the unit vector R hat, which is just going to be the opposite of the electric field vector. So we can say then that the electric field vector is equal to minus dV dr in the direction of r hat, the electric field from the voltage function. That's going to come in useful later on. Let's see if we can't continue these derivations by finding the getting the electric potential from the electric field. We've already talked about potential being the work done divided by the unit charge, or that's 1 over the charge times the integral from r to infinity of the electric force dotted with dr. So we could pull the q back inside here and say that that's the integral from r to infinity of the electric force divided by q dotted with dr. But if you recall, the electric force divided by q is the definition of the electric field. E equals Fe over q. Therefore, we could say then that our voltage is going to be the integral from r to infinity of E dot dr. If we wanted to go a little bit further, talk about the change in potential, the potential difference, oftentimes much more applicable. That's going to be change in voltage, VB, voltage at point B minus the voltage at point A. That's just going to be the opposite of the integral from A to B of E dot, I'm going to change our variable to dl, the integral along that line, dl, which is the potential energy, change in potential energy divided by the charge. So voltage is the opposite of the integral of E dot dl, which is the potential energy divided by that charge. Let's put this into practice with a couple sample problems now. See if we can't tie all this together. So let's find the potential due to a collection of point charges. Find the electric potential at the origin due to the following charges: plus 2 coulombs at 3, 0, minus 5 coulombs at 0, 5, and plus 1 coulomb at 4, 4. Well, our electric potential is just going to be 1 over 4 pi epsilon naught times the sum over all I of qi over ri, which is 1 over 4 pi epsilon 0 times, let's add up all of our q over r's. Our 2 coulomb charge is going to be 2 times, I suppose these should have been microcoulombs, 2 times 10 to the minus 6, let's make those all microcoulombs, divided by 3 plus negative 5 times 10 to the minus 6, and its distance is 5, plus we have 1 times 10 to the minus 6, making these all microcoulombs again, at a distance. Well, to get the distance from the origin for a point at 4, 4, we've got to use the Pythagorean theorem. That'll be the square root of 4 squared plus 4 squared. Plug all that into my calculator, and I come up with a potential of about negative 1410 volts. All right, let's find the electric field from the electric potential. Given an electric potential function, V of x is equal to 5x squared minus 7x, find the magnitude and direction of the electric field at x equals 3. Well, the first thing I'm going to do here is I'm going to write down my relationship. The electric field is equal to minus dV dr in the direction of r hat. And in our case, that's going to be minus the derivative with respect to x, because this is a linear function, of 5x squared minus 7x in the direction of r hat, or in this case, that's just I hat. So I take the derivative minus, derivative of 5x squared is going to be 10x, and the derivative of minus 7x is just going to be minus 7 I hat, or multiplying the negatives through, we get 7 minus 10x in the direction of I hat. But we also know we want to find this specifically when x is equal to 3 meters. Therefore, we can say that the electric field at that point is going to be equal to 7 minus 10 times 3 is going to be 30 times I hat, which is going to be minus 23 volts per meter, or newtons per coulomb, equivalent units, in the direction of the I hat vector. All right, let's keep going. Let's find the speed of an electron that's released in an electric field. An electron is released from rest in a uniform electric field of 500 newtons per coulomb. What is its velocity after it has traveled 1 meter? Well, this sounds like a conservation of energy sort of problem, where our change in kinetic energy is going to be equal to the opposite of our change in potential energy. But we know that the change in potential energy is going to be minus Q integral from A to B of E dot dr. Therefore, our change in kinetic energy must be Q integral from A to B of E dot dr, which implies then that our change in kinetic energy must be equal to, well, we can pull the electric field out of the integral sign because it's a constant in this problem, so that must be Q times the electric field integral from A to B of dr, which is just going to be delta R, your change in R. So that's QE delta R. Therefore, well, let's get back to our kinetic energy. Change in kinetic energy, if it starts at rest, that's just going to be 1/2 m times our final velocity squared for our electron must equal QE delta R, or solving for velocity, that will be 2 QE delta R over m square root. Now we can substitute our values in. That will be 2 times the charge on our electron, 1.6 times 10 to the minus 19 coulombs. Our electric field was 500 newtons per coulomb. We also have our delta R, 1 meter, divided by the mass of an electron, 9.11 times 10 to the minus 31 kilograms. We need the square root of all of that, which comes out to be about 1.33 times 10 to the 7th meters per second, assuming we're ignoring all relativistic effects. Great. Let's try one last sample problem. 2 point charges, 5 microcoulombs and 2 microcoulombs, are placed 1/2 meter apart. How much work was required to establish that system? Well, to begin with, let's figure out that the potential energy, the electrical potential energy, is just going to be 1/4 pi epsilon 0 times Q1, Q2 over R. So in this case, that's going to be 1/4 pi epsilon 0. Q1 is 5 times 10 to the minus 6 coulombs. Q2 is 2 times 10 to the minus 6 coulombs, all divided by the distance between them, 0.5 meters, or 0.18 joules must have been required in order to establish that system, to get those charges in place. Let's take this same problem just one step further and find out what the electric potential is halfway between the two charges. Well, if we want to do that, the electric potential is going to be 1/4 pi epsilon naught Q1 over R plus 1/4 pi epsilon naught Q2 over R, where now our R is 0.25. So that's going to be 1/4 pi epsilon naught times our 5 microcoulomb charge divided by its distance from the point that we are concerned with between those two, plus the 2 microcoulomb charge, 1/4 pi epsilon naught times 2 times 10 to the minus 6 divided by its distance from that halfway point, 0.25 meters, plug all that into my calculator, and I come up with something near 252,000 volts, or 252 kilovolts. Hopefully that gets you started on electric potential energy and electric potential, especially with respect to point charges. In our next video, we'll talk a little bit about how we deal with these in continuous charge distributions. Thanks for watching, and make it a great day.